Last class we have started with the 3D object representation. So in which it is broadly classified into 3D object, or the basis of 3D we have discussed, and then we have discussed how to represent or a model a 3D objects. In the case of 3D object representation, it is broadly classified into two categories. One is you can draw the boundaries for the space partitioning methods you can use to construct the 3D objects, and we have discussed the different categories of 3D object representation: polygon and quadric surfaces, spline and Bezier curve representations, and the procedural method for generating fractals, and octree method yet to discuss. So the octree method, which uses the internal features of an object to represent it. So I'll be discussing that. Before that, we will discuss the problem on Bezier curve. So already we have discussed what is control points, convex hull and control graph, and all we have discussed, and also we have discussed the property of Bezier curves. So with that, I am moving on to the problem. It uses a parametric continuity condition and geometric continuity conditions. 0, first order and second order in both parametric and geometric conditions. Yes. So we can able to get the PU. PU is the position vectors by using this equations. So in which where the blending function is given as this one, the Cnk is a n factorial by k factorial into n minus k factorial. So with this we are moving on to one example problem. Determine the parametric equation for cubic Bezier curve. So it says it's a cubic Bezier curve. The number of control point equal to 4. The definitions in the case of control point. The Bezier curve can be fitted to any number of control point given n plus 1 control point positions. So we are using n control points to place it because it starts with 0 to n. So in this equation we are going to substitute and we are going to find out what are all the values we are obtaining for it. So for we have PU equal to summation of K0n. Summation of this value will gives you 1. Already we have discussed this. So we have an PK, where PU is an any point lying on the Bezier curve, and this is the blending function, and n represents the degree of the curve, which is total number of control point minus 1. Degree of the curve is n. Pk, this Pk is kth control point on the Bezier curve. Is the notations are clear? Bu, any point lying on a Bezier curve. Pk is the ith control point on the Bezier curve. N is the degree of the curve, and this term, entire term, is the blending function that we are going to use, and where this blending function in this, which is equal to, it is specified here, n minus k u k, n minus u, n minus k, where this portion is so with this definitions, we will move on to the problem. The derivation, we are trying to derive the parametric equations for the cubic Bezier curve with control point of 4. So it is now from this, it is says it has 4 control points. So n is total number of control point minus 1. So with this we can able to write pu, which is equal to k0 to 3 pk k of 3 of u. We can expand this. So after expanding, you will be getting 0.3 of u plus b1 u plus b2 2 of 3 plus, so we have totally 4 terms in it. We need to find out these terms, and we can say those are the parametric equation or positions for the PU positions we are trying to get. So to obtain this position, this value should be known. What is this after substitution? This in this equation 1 and 2. So we have expanded equation 1. In equation 1, again we need to expand these terminologies. So finally, whatever you are getting, whatever PU you are getting after substituting these values, that is going to be your final function. So what is the value we have for this? Just substitute in this and tell me the value for each and every terms. Substitute this in this equation and tell me what is the value we have for this. I'm waiting for the result. Are you doing it or you want me to do that?
We are doing that.
Yeah. So tell me the result for these things. So one can do this portion and some people can do the second and some people can do the third and fourth, so that the process will be easy.
First is 1.
1.
And even the last is 1.
Last is also 1. Intermediate. Are you substituting this value also? This entire term you have to do. Are you getting only 1? What about this terms?
Oh, okay, okay. I used only the first value. Sorry.
You have substituted only with the combinations.
Yeah.
The entire term.
Yeah. Okay.
So the combination value for this term is 1 and remaining you will get
1 minus u whole cube.
Whole cube, yes. And second?
And for the last, it should be u cube.
U cube, yes.
Second and third I will do it till now.
Okay, second and third I'll just give you. You can verify it later. It's 3u into 1 minus u whole square, and the third one is t u square minus 1u. So these are all the values we have obtained. So add all these value. What is the value you have obtained for this? If you add all these values, maybe you can do it. So as per the definition, it says sum of all these values will be equal to 1. Obviously you can expand it and you can check it out whether you are able to get the value later point of time. So this is the parametric equations that we have obtained for this. So the blending function determines how the control point influences the shape of the curve for the value of the parameter u over the range 0 to 1. So for the value of u will be 0 to 1, ranges from 0 to 1. So the value of, based on the value, it is changing the shape of the curve. That is the explanation I wanted to explain you here with respect to the Bezier curve. Normal polygons, 3D polygons, and then we have discussed quad surface representation, quadric surface representations, spline representation, and Bezier curve representation, and fractal representation. And again, we are moving on to octree. This is the last representation that we have. So octree, and one more thing I'll explain later. When it comes to an octree representation, first I will be talking about an quadtree. It is an extension of a quadtree. When you talk about quadtree, it's an 2D representation. You have 4 regions. 4 regions. Each region is divided into an equal halves. Further, any region can be further divided into 4 equal halves, and further you can divide until you get an homogeneous pixel. You can start dividing it and you can able to get the information. The quadtree encoding divides the square region of space into 4 equal areas until the homogeneous regions are found. So an example is specified here. You can see the regions are given here. It is further divided. So you can see it's a different color. Further you will get a homogeneous coordinate. You will start dividing it. With respect to 2D. When it comes to 3D objects, you have to use quadtree. It has all the 6 faces and you can start dividing it. So it starts with 0 to 7, all the values will include it, and it will be divided as we have done in the case of an 2D to get the final representations of a 3D objects. In the case of 2D object, we will call the pixel information as a pictorial information as an picture element or a pixel. In the case of 3D, we will call it as an volume element. And another representation, this also uses a kind of 2D representations only, sweep representation, which uses a translation, rotation, and other symmetric transformations for constructing a 3D objects. So initially we'll start up with an 3D, and that will be made it as a we'll start up with a 2D that will be made as in 3D objects. The objects are specified as in two-dimensional shape, and sweep that moves that shape over the region. The operations we can do is either you can rotate or you can perform some translation or symmetry property to get the 3D objects. So this is the sweep representation, and one more is in solid construction of solid geometry. So construction of solid geometry uses constructive solid geometry method, which uses the operation set operations. The operations we can use here is union, intersection, and then difference. So constructive solid geometry combines the volume occupied by overlapping 3D object using union, intersection, and the difference operation. So let us consider a object. It's an 3D objects, and again you have another object. So two 2D objects you have. This is object 1 and object 2. By making use of an union, you can construct a single object so that this will fit with this, and you will able to get the output object as this. Similarly, when object is this is one object, the other objects overhides this object. So after applying intersection, you can able to produce the intersection region only as the output. So this intersection region will be your output 3D objects output. And the third representation is difference. You can make use of a difference. Only the difference value will be counted here, and this portion, whatever the remaining portion is there, that will be constructed. So with this, we can able to construct solid geometries of different objects. So with this representations, we are concluding the 3D modeling part. We are moving on to the transformation part. So the preliminaries we have started with the definitions. What is a 3D object? How it will be represented? What are all the property a 3D object consists of, like projections and rendering, all those things we have touched up. And then we have moved on to the viewing part. In the viewing, modeling 3D objects and representing the 3D object we have discussed. And then we are moving on to the transformations. As similar to your a 2D transformation, 3D also uses the same set of transformations, except that it has one more coordinate value, which is Z coordinate. So this is the original point. We have an object here. This is a point we have, original point. After translating with the translation factor of Tx, Ty, Tz in the respective axis, the original point is moved to x dash, y dash, and z dash location. So this is your P, and you are getting P dash by adding the corresponding translation factors into the corresponding axis. So with respect to point this, when we talk with respect to object, all these coordinate values are added with the translation factor, and it will be moved to this position. When we are, as we know that the operations uses composite transformations also to make the computation in an easier way to avoid the intermediate calculations. We are representing everything in the form of matrix. So when you represent in the form of matrix, again the problem of addition. Only the translation uses a addition and remaining uses a multiplication factors. To make everything into one common matrix, we have converted everything into one homogeneous coordinates, and then we have started the process. So here you can see this is your P dash equal to P into T. As I told you earlier, the representation is very important. In what way you are representing, whether you are representing in a row wise or a column wise, based on that it will provide you the result. So when you are representing in a form of in a row wise, this is the form. When you are representing in a column wise, you will be getting P dash equal to T into P for column representation if you represent it in a column wise. So the first the matrix, and then you need to represent the pixel coordinate, and this Tx and Ty will be occupying these positions in the case of column representation. So be clear, because we are going to perform the multiplication operations. Multiplication of matrix is not a commutative property, so based on the representation only it is going to give you the result. So be clear with the notation, how you are going to notate it, whether it is a column or a row wise notation. Next, coming to the rotation. In the case of rotation, in the previously when we talk with respect to 2 dimension rotation, we will be talking about a theta. Theta can be either a positive value or a negative value. If it is a positive theta, then we are performing a anti-clockwise rotation, and if it is negative theta, we are performing an clockwise rotation. So same thing is applicable here also. And how we are going to rotate the object, whether you are rotating in z axis or with respect to x axis or with respect to y axis, we are going to rotate it. So the rotation with about z axis, so when we rotate it, the z axis value remains same, and the other axis values will be x dash equal to x cos theta minus y sin theta, and y dash equal to x sin theta plus y cos theta, same thing. And when we apply the rotation with, so the example is also specified here. After rotating this object of some angle theta, it is rotated and it is kept like this. So when we wanted to make a rotation with respect to x axis or y axis, so when we make the rotation on z axis, only x and y plane component will be there, z component is not there, and because it is same. And the other, similarly for other cases, so easily we can make out the other equations, other axis, by cyclic permutation of an coordinate parameter x, y and z, by which we can able to write it. Wherever we have x, x can be replaced with y and y can be replaced with z, and likewise we can get it to get the other axis value. When we are rotating with respect to x axis, x value is remain same and y value will be y cos theta minus z sin theta, and z dash equal to y sin theta plus z cos theta, and after rotation the object is represented. In the case of rotation about y-axis, we are rotating with respect to y-axis, so y-axis value remains same and the other two axis values are only will be there. We will get y dash equal to y, x dash equal to z sin theta plus x cos theta, and similarly z dash equal to z cos theta minus x sin theta. The rotation can be about any axis. So if you are performing a rotation with respect to any axis, with respect to P1. What we have to do is we need to move this line such that it passes through the center and try to fix this line to any one of the axes. Either it can be x-axis or y-axis or z-axis by making a rotation of either positive or negative theta, and then you can fix this with any one of the axes, and then you can perform the rotation with respect to the corresponding axis. So you can fix with this, and then you can perform a rotation with respect to this axis, and you can able to get it. Once you have obtained the result, apply inverse rotation and inverse translation to get the result into an original place. So a set of composite transformations are used to make it with respect to some arbitrary fixed point. And coming to the scaling factor is simply multiplied with the each and every coordinate value. X dash equal to x into, this is x dash, and this is y dash and z dash. Directly you can multiply and you can get the result. So have started with the viewing coordinate, and we have discussed this viewing coordinate in last class. If suppose the point is all the equations what we have discussed till now is with respect to the origin. If it is not with respect to the origin, if it is with respect to some arbitrary point, we are trying to fix this with this point, and then we are making the axis to coincide, and then we are performing the operations. Transformations are there. The other two transformations are shearing and reflection. Reflection, in the case of reflection, as we discussed earlier, we can make a reflection with respect to x-axis or y-axis or z-axis. So here in the case of a 3D object, when we wanted to reflect it, the reflection plane can be xy plane or yz plane or xz plane. We can perform reflection on any of this plane. If we are performing reflection on xy plane, so the xy value will be same and the z value will be reversed. So we can make a reflection matrix. XY value is same and Z value is negative of the value. So this is the reflection matrix with respect to Z axis, and we can represent this in the form of an homogeneous coordinate also. This is the homogeneous coordinate. Similarly, the reflection with respect to XY plane, which is reflection with respect to YZ plane. So the reflection with respect to YZ plane, X value is changed and the remaining values will be same. With respect to this, so the reflection, the value Z value is changed, X and Y value is same. Here X value is changed, Y and Z value is same. This case Y is changed, X and Z is same. So by which we can make out the reflection. And if you wanted to make a reflection with respect to some line, any line y equal to mx plus c, the same composite transformation steps can be applied. Translate that line such that passes through the origin and rotate it, fix with any one of the axes and try to reflect with respect to that axis and put back the result to the original place by applying inverse rotation and inverse translation. In the case of shearing, the last transformation, shearing, again same way we can perform the shearing. Just I will be giving you a shearing with respect to Z axis. So Z axis shearing either you can make with respect to X axis, Y axis. So with respect to z axis, so x value, y value and z value. Z value remains same and x dash and y dash value is x plus z multiplied with the x sharing factor. When it comes to y coordinate, y plus z coordinate value multiplied with y axis sharing factor. So similarly, you can able to write down for x and y coordinate by changing their corresponding values. So we have now discussed different types of sharings. Problems are same as we have discussed with respect to 2D. Only the information, whatever the matrix we are going to represent, that is going to be different here. And so I am not discussing problem right now. I am moving on to the projections now. Coming to the projections, there are two kinds of projections we have, and also we should know some preliminaries related to the projection. When we talk about the projection, three important points we should know, that is center of projection, projection plane or view plane, and the projector. These are all the three important points that we should be able to know. The center of projection. Center of projection, the point from where the projection is taken. It can be either a light source or from eye position. So this position, eye position or a light source can be the center of projection. And the projection plane, the plane on which the projection of an object is formed, is the projection plane or view plane. The projectors, this is the object that we are going to project it on the plane. The projector or the line emerging from center of projection and hitting the projection plane after passing through the point in an object to be projected. So based on this, we are categorizing the projections into different categories. Categories of projections are parallel and perspective projection. Under parallel projections, we have orthographic projections. In the case of orthographic projection, we can able to get either front or top or a side view or bottom or a rear views. And another category of parallel projection is axonometric projection. It has further classified into trimetric, dimetric, isometric. And the third category of parallel projection is oblique projection, cabinet and Calvia projection. And coming to the perspective projection is categorized into three, 1 point, 2 point and 3 point. So we are going to discuss each and every projections and with example problems. The plane geometric projection of objects are formed by intersection of a line called projectors or on the plane called projection plane. So the projectors are a plane from arbitrary point called center of projection through each point in an object. If the center of projection is infinite distance in 3D space, the result is an perspective projection. If the center of projection is if it is in finite place, then you can call it as an perspective projection. If it is an infinite place, you can call the corresponding projection as an parallel projection. I'll show you an example, then it will be clear to you. You can see P1, P2, and this is projecting it here. When you draw the lines, all the lines are parallel, it is not going to be converged anywhere. So this is called a parallel projection, whereas perspective projection, you can see it is converging in one point, which is called projection reference point. The center of projection is at infinite in the case of parallel projection. All the projectors are parallel to each other in the case of parallel projection. Whereas in the case of perspective projection, the center of projection is in finite distance. The projectors are not parallel. The same thing what I have explained here is given here. So last class I have showed you an example. Based on the projection point, you can see a different posture of an object. Either you can see a top view or a bottom view or a right side or a left side view. Whatever view we wanted, we can display it and we can view it based on the projections. So based on that, the orthographic projection is specified. I am again talking about two more aspects in the case of projection. Let me take any object. Let me take an object. So now this is the object we have, and from here you are viewing. So let us consider the center of projection is from your side and this is the object we have. There are two ways by which we can view the object. Either you can keep this object as fixed position, or you can keep the center of projection point as in fixed position. Suppose if you are keeping the center of projection as fixed, I have the flexibility of moving the object itself. Either the object can be moved or the center of projections can be moved. Right now your eyes are kept fixed and this can be rotated so that you can able to view the different portions of the object. Any way I can rotate it. If you wanted to see the top view, I can rotate it this way. If you wanted to see the back end, I can rotate it. So whatever you wanted, you can rotate it, you can move the objects and you can see the different views of this object. And in this case, the object is rotating, but the center of projection is fixed. Second case, this object is kept fixed and the eye is rotating. I can rotate and I can see the different postures, whatever it is represented here. It's clear? There are two ways by which we can view the objects. Either we can rotate the object and you can keep the center of projections as fixed. In second category, I have considered I am the center of projections and the object is kept as such, and you can rotate the center of projections can be rotated and you can see the different postures of the object. So these are all the two ways by which we can do that. So in our subject, we are going to fix the center of projection and the object is going to be moved throughout the whatever the discussion we are going to have. That is the discussion. The second approach, the center of projection is kept fixed and the object is movable. That is the approach we are going to use throughout our discussion. So next class we will discuss different types of projections, that is how the orthographic projections is providing the different views, and with some problems we can explain it. we can discuss it. Thank you.
Thank you, ma'am.
Thank you.
Thank you.